Here goes. Section 7.5, improper integrals. For our unit on integration, we discovered that the definite integral was defined as a limit of Riemann sums. Riemann sums, do you remember them? The LRAMs, RRAMs, MRAMs, that's Riemann sums. We use the fundamental theorem of calculus to evaluate definite integrals, and now we want to explore some integrals that don't meet the conditions of what is called a proper integral. So what's a proper integral? Everything you've seen so far is a proper integral. So an integral that has bounds, a to b, is considered a proper integral if the limits of the function are bounded. Proper integrals are always well defined. In other words, the limit you get an answer, you get a number answer. It converges. It converges to a particular number. So the function is defined and bounded between a and b. The limits of integration are finite. They're numbers. Your bounds are numbers, not infinity signs. And the function has only finitely many discontinuities in the interval. That's talking about how, you remember how like with an integral you can break it up where it crosses the x-axis? You can break it in pieces. That's what they're talking about. That wherever you're allowed to break up the integral into separate parts. So in this lesson we investigate what happens when these conditions are not met. These are improper integrals. They're improper if one of two things occurs when defining the integral. The first type, and this is the type that's most popular, type 1, is when your bounds are infinity or negative infinity. So this is important. If you get a bound that's infinity or negative infinity, it's automatically an improper integral, and you'll know you need to take this set of steps to be able to solve it out. I'll tell you the set of steps in a minute. Or type 2, the region defined by the function has an infinite discontinuity. An infinite discontinuity, you say, what the heck does that mean? And so my answer to you is, do you remember the old I can't touch this graph, right? If my function, the one that's on my wall in my classroom that we can't see, one that's 1 over x, what does that look like? I'm just going to draw the first quadrant part of it. But see how this one has an infinite discontinuity? It's got a vertical asymptote. That's what really this is talking about. An infinite discontinuity is like having a vertical asymptote. And so the question is, like if I were to ask you to figure out what the integral is from 0 to 1, can you do that? Because see how the function goes to infinity and there's always going to be a little space between it and the y-axis? There's always going to be a space there. So can you figure out that area if there's a space there? And you actually can, but it involves this whole deal of improper integrals. So these would be the two cases. If your bounds go to infinity, one or the other, positive or negative, or if you end up with having a vertical asymptote that you're trying to find an area near, they're improper integrals. So they're going to start out with us. Sketch the infinite region R that lies under the curve of y equals 1 over x squared above the x-axis, and then shade the area to the right of the line x equals 1 and ending to the right at some value of t. All right, can we do that? Let's take it one piece at a time. If I am 1 over x squared, 1 over x squared is the same thing as this guy up here, 1 over x, except the second part, you know how normally the second part's down here in the third quadrant? If it's x squared, then everything has to be positive, so it will be up here in the second quadrant. So it will be this first quadrant and second quadrant, that's 1 over x squared, but they only want us to do it in the part that is above the x-axis to the right over here. So they only gave us this first quadrant, guys. So it looks like this. That's my 1 over x squared. Y equals 1 over x squared. And then it says, okay, well, shade the area to the right of the line x equals 1. So I'm going to make my line right here. This is 1. Here's my line. And ending to the right at some value of x equals t. So I've got another line over here somewhere at x equals t. And what they want me to do is to shade this thing. Shade the area. Pretty. All right, got the picture. Then they want us to then solve the integral. Well, remember that this would be the same thing. If this is the integral, if this is my integral, it's the integral from 1 to t. Thinking that I'm going to have to antiderivative this, I'm going to put it into a form that's going to help me with my power rule. So x to the negative 2 dx. Levi just came by and he's throwing his toys at my feet. What do you think he wants? I should get him together with Brenna's doggy. All right, let's see if we can antiderivative this. So if I take x to the negative 2 and I add a power on and divide by that power, that gives me my integral. So I'm going to have a negative x to the negative 1 going from 1 to t. Agreed? Add a power on, divide by the power. And now I'm going to f of b minus f of a this thing. So f of b, I put a t in. That's going to be a negative t to the negative 1 minus f of a. That's going to be a negative 1 to the negative 1. Which, if I make it prettier, let's see, negative t to the negative 1 is going to be negative 1 over t. And a negative 1 makes this plus 1. Do I need a plus c?
No.
Good answer. No is correct. Right, I have bounds. Do you have bounds? Do you not have bounds? So because you've got bounds, you don't need the plus c. That really is actually what your answer is. Okay, so that would be what the area is represented by in this particular case. So what does the answer tell you about the value of a of t? A of t. In other words, what does that tell you about the value of this integral? What do you think that this number is going to be really close to? Now think about that logically. Okay, guess it's out there of 0 or 1. Okay, there's some zeros, there's some ones. Good thinking. Okay, you're in the right neighborhood. You are all, it's going to be small. Kat's going safe. She's just doing generalities there. It is going to be small, and it actually, 0 and 1 are the two things that you should be thinking about. So think about a t value. Think about if t is, I don't know, what do you want t to be? If t is 2, then your answer would be a positive 1/2, right? If t is 10, it's going to be closer to 1. If t's, how about if t's like infinity, right? If t is some humongous answer, this fraction becomes 0, which means that your answer is 1. So if I'm looking at this, the answer to a of t is going to be close to 1, depending on what that t value is. Is it ever going to be bigger than 1? Can it be bigger than 1? I don't know.
If it goes towards negative infinity, yeah.
That is true, but check out my function. Right, my function's over here in this first quadrant. So because of that, you're right. Good thinking, because that would be a negative negative, making it positive, making it bigger than 1, yeah. So if I'm looking at the graph, it's only in this first quadrant area. So it's going to be close to 1, so the limit exists. So a of t is always going to be close to 1, and if you get an actual answer out of this, then because the integral exists, then the limit exists. And that's what they're trying to get you to see with this. So then it says, all right, well, find the limit of this. Find the limit of a of t. Let's check it out. So find the limit. That would look like this. The limit as t approaches infinity of what is a of t. We decided a of t back here in part A of negative 1 over t plus 1. So I substitute in, like we did, kind of talked about it. If I have negative 1 over infinity plus 1, I really have 0 plus 1, so I get an answer of 1. All right, so that's your first example that they're talking about.
Miss Winter?
Yeah.
What if t was heading towards 0?
If it were on the other side over here?
Yeah.
It would change things up a bit. It would change, you know what it would change? Your bounds. So now you'd have your bounds, the bottom bound would be t and your top bound would be 1.
Uh-huh.
Which then, when you f of b minus f of a, is going to change up your equation a bit.
Okay.
Yeah. It just would change your bounds, which then, like I said, would change up your b and your a.
Oh, okay. Yeah.
All right? Okay, so let's flip the page, and now she's going to give you some math gobbledygook talk. And I'll see if I can decipher it into English for you. All right, so case 1 and 2. The improper integral, they're using these words converge and diverge. They come up a lot when we get into studying sequences and series. Does something converge or does it diverge? So the difference is, for something to converge, it has to be approaching a number. So like the last one, everything was approaching 1. That's a converging situation because you get an answer of 1. If it is not converging, like not moving towards a specific number, then it's called diverging. Most times these are going when they're going towards infinity. You can't, if you're thinking about something when you're solving an equation and you get an answer that goes to infinity, you don't know what infinity is. So therefore it's a diverging situation. It's not converging like it would if you could solidly solve it and get a number answer. So that's really the difference. Do you get a number answer or do you get something crazy that you can't even zero in on? Okay, that's the difference between those. So this improper integral requires both of the integrals to be convergent. They both have to be approaching a number in order for the integral to also be in order for the improper integral, both have to be convergent for the integral to also be convergent. If either of the two integrals is divergent, then the integral is also going to be divergent. We'll talk more as we see the examples. So continuous looks like this. Continuous from a to infinity. Continuous from negative infinity to b looks like this. Continuous from negative infinity to positive infinity, you have to split it up. That, again, is not going to make a whole lot of sense until you see some problems. So here's the deal. Remember that evaluating an improper integral is really 2 problems. It's an integral problem and a limit problem. That's important to us. It is best to evaluate them separately. Do them separately. And when breaking down improper integrals, be sure each integral is improper at only one place. In other words, you can only have an infinity. You can't have an infinity at the bottom bound and the top bound. It has to be broken up where there's only one infinity involved as your bounds. That's what she's trying to say here. That one place should be either the lower limit of integration or the upper limit of integration. That's your infinity signs. They can only be in the top or in the bottom, but not both. So I get to this first example, the 1 over x. They can't touch this graph. Now here's what I want you to, off to the side here on the right. This is what we're going to do. These are the steps. You ready? Step number 1. You want to write as a limit at an arbitrary x value now in this case I'll put a little parenthesis, either a or b. I should say an or, not a. Let me write it so it doesn't look like a coordinate. And then you're going to integrate. And then you're going to evaluate. And then you're going to find the limit. All right, so here's how it works. We're going to take this one as a relatively easy one. This one is considered to be an improper integral because it has infinity as its upper bound. That means that that is the b value, right? If I'm thinking about an integral, the bottom value is your a value, bottom bound, top bound is your b value. So the fact that the infinity is in the b place, I'm going to write my limit using the letter b because that's where the infinity is. So here's how the limit would go. This equals the limit as b approaches infinity for the integral going from 1 to b of 1 over x dx. All right, so that's step number 1. Write as a limit at an arbitrary x value, which you're using a or b. We're changing the infinity to a b because it's in the upper bound place. And now I want to integrate. So forget about all this other stuff. What is the integral of 1 over x? Do you remember going backwards? He's got like a special case. You're not going to power rule him. Do you remember? He's an ln of x?
Yeah, ln.
Yeah, ln of x. I'm putting the absolute value signs in there because, you know, technically you need them. Now I'm going to evaluate the integral, and that, in other words, I'm going to f of b minus f of a it. It's still a limit as b approaches infinity. It's all this notation you need to keep writing each time. And I'm going to do my thing here. ln of the absolute value of b minus the ln of the absolute value of 1. Before I actually find the limit, does any of that simplify?
ln of 1 becomes 0.
Yeah, ln of 1, this guy's a 0. Right? Anything to the 0 power is 1, so you end up with that. Since you're talking logs going backwards, it would be equal to 0. So really what I'm taking is the limit as b approaches infinity of the ln of b. Now I'm finding the limit. Well, when you find the limit, you're plugging in infinity for that place. So if I take the limit of as b approaches infinity for the ln of b, that would be the ln of infinity, right? Plug it in. Direct substitution. What's the ln of infinity?
Does ln have a horizontal asymptote?
That's a great question because the ln graph actually, if I were to do a quick little graph of it, it looks like this, right? So it kind of, it does not, the answer to your question is no, it does not have a horizontal asymptote, but it does grow slowly when you get off to the right, and it grows slower and slower the further right you get. It's not like it increases rapidly like the exponential graph does. So this guy, yeah, he does kind of, goes horizontal on you, but he's always growing at some rate. It's just not by much the further right you go. So it kind of appears that it might have a horizontal asymptote, but it really doesn't because it keeps getting taller. So if that's the case, then this is going to be infinity, right? It's going to keep growing, but it's not growing by a lot, but it's still growing and getting bigger. So it goes to infinity. Now let's talk converging or diverging. If something is going towards infinity, can you tell me what it is? And you can't. So that means that this guy is an example of something that diverges. Therefore, my 3 dots, it's a diverging thing. If I got a solid number answer, then that would be converging. This one is going to infinity. I get an answer that's diverging. So they're the steps. We're going to write them as limits, changing the infinity to an a or a b, depending on where it's located in my bounds. Then you're going to integrate it. Then you're going to evaluate it, f of b minus f of a, and then you're going to find the limit at the end. Okay? Improper integrals. Let's see if we can grow on that. Example 3 is next, and in order for me to write it big enough for you to be able to see it, I put another piece of paper here. Because example 3, obviously, they're not always going to be that simple, right? Ain't nothing that simple.
Swear?
Yeah.
Would we still have to split it up if it was like positive infinity to positive infinity?
Well, that's a great question. Positive infinity to positive infinity would be an answer of 0 automatically. Remember that? Like, because it's going, there is no area. It's like going when your bounds are 2 and 2. It doesn't go anywhere. But I think your question really is, if it goes from negative infinity to positive infinity, then yeah, you got to split it up. And that's going to come into play with example 4. So if you look at example 4, he's one of those that your A bound is negative infinity and your B bound is positive infinity. That's got to be split into 2. All right? So we'll get to him in a minute. We're still working on example 3. So example 3 has a whole bunch of stuff that comes into play, but let's do our rules, right? If I write it as a limit first, now where's my infinity? My infinity is in the A location. So now my limit's going to be the limit as A approaches negative infinity for the integral going from A to 0 of x e to the x. Do you see how the writing of that limit goes, right? So step 1 is write it as a limit. But step 2 says, all right, now integrate it. And you look at that, and my children, what do you think? How do you integrate that? Yeah, I'm here. Yeah, exactly. Great. Oh, that's awesome. I'm glad you're thinking of this. That's exactly a tabular. Tabular would be your easiest way to integrate this one. Okay, you could use a U substitution probably on it too, but I like the tabular idea, so I'm going to come over here to the right a little bit, knowing that I have to integrate, and I'm going to have one piece as my x, and then the second piece is my e to the x. And then I have the plus or minus 1s, which we'll come to in a second. So the derivative of x is 1, the derivative of 1 is 0, the derivative of e to the x is e to the x, right? And I'm coming down the line here. If I go, this would be a 1, this would be a negative 1, and now I'm going to put my rows together with my highlighter here. And then the other one zeroed out, which is sweet. Okay, so I'm going to put this together, and I know now what my integral is going to be. So I still have the limit notation. The limit as a goes to negative infinity of the integral. Oh, wait, no, I don't need the integral anymore. Right, because I'm going to put it out here. It is x times e to the x times 1. So it is an x e to the x. And then it is a minus negative 1 times e to the x times a negative 1 makes this a minus e to the x. And that is going from a to 0. Okay, we integrated. That's step 2. Now we're going to evaluate. So we're going to put in our zeros and our a's. So we're going to f of b minus f of a this. It's still a limit. I haven't taken the limit yet. It is going to be, let's see, 0 times e to the 0 minus e to the 0 minus, let's see, a e to the a minus e to the a. Well, if I look at this, I know that obviously this first term zeroes out, right? E to the 0 is 1. So in this first part, if I were to simplify this one more time before I take the limit, I have a negative 1. I have a minus a e to the a. And I have a plus an e to the a. And so now I'm ready to take the limit. Well, putting in an infinity into this is where I'm going to go with it. Now you have to think of, does this confuse, it can be a confusing thing. If I think of the e to the a graph, and I'm trying to put in a negative infinity into that. If I think of the e to the a graph, it's an exponential graph, correct? So if I think graphically about this thing, any exponential graph is going to go like this, correct? Right? You're talking about an exponential grow. So e to the whatever the a is going to be, I'm at negative infinity. If I go really far to the left towards negative infinity on this graph, what happens with all of the values? The y values are getting closer and closer and closer to, yeah, they're getting smaller. They're getting closer to 0, right? So that means that this guy zeroes out, and so does this guy zero out. When I put a negative infinity into these places, negative infinity would be way far to the left of that guy, and that's going to be a value that zeroes out. So what does this limit actually equal? It actually equals 1, negative 1. It only equals this guy right here, negative 1, because these guys both zero out. Then the question is that an example of something that converges or diverges? And the answer for this one is going to be converge, because you got an actual number answer. So if they ask you the question about is it divergent or convergent, you can say that one's convergent because you got a number answer. All right. Here comes example 4, which again, I feel like I need more space than just what that box gave me on that one, because this one takes a little bit of doing. And I know that it takes some doing because look, I've got to split my bounds up into 2 different integrals. So before I even start all this changing it into limits, I'm going to play around with the original function, and I'm going to change it right up into, this would be the same thing as me saying negative infinity to 0 as one of my integrals. Function stays the same. And I'm going to add that with the second integral going from 0 to infinity. So that's my first split. Maybe I need to separate that. Now I'm ready to write it as the 2 integrals that it's, or 2 limits that it's going to be. This one is going to be my a value. So this one's going from a to 0. And this one, my limit's going to be using, this is my b value. Okay, so my first limit, if I put it over here, limit number 1 is when a is going to negative infinity of the integral from a to 0 of my function. And I'm adding that with the limit as b approaches infinity for the integral going from 0 to b of my function. You're going to stop me if you get stuck on the way where we're going. And my hope is, if you can remember, maybe you need your cards, what's this look like for an integral? What's the integral of 1 over 1 plus x squared?
Tangent of negative 1.
Yeah, the inverse tangent. Yeah, yep, I know exactly what you mean. Yeah, exactly. This is an inverse tangent guy. So when I go to now integrate, which is my next step, right? I have the limits all written out. Now I want to integrate this. This is going to be like taking the limit as a approaches negative infinity, but my integral is tangent to the negative 1 of x. And that one's going from a to 0. And lucky for us, it's exactly the same for the second part. So I've got the limit as b approaches infinity for the inverse tangent going from 0 to b. All right, let's f of b minus f of a each of these. So here it goes. I'm still got the limit notation going on. So tangent to the -1 of 0 minus tangent to the -1 of a plus the limit as b approaches infinity for tangent to the -1 of b minus tangent to the -1 of 0. I don't know whether this is a calculator question or not, but here's what the story is with the inverse tangent graph. I'm going to talk about the graph first. Do you remember how tangent graph goes? If I were the tangent graph, this is tangent. He goes through the origin like this. Where are his asymptotes? So he's got an asymptote over here, he's got an asymptote over here. Those are at the pi/2 locations. Does this ring a bell? This guy is x equals pi/2. This guy's x equals -pi/2. Well, when you do the inverse tangent, your x's and your y's have switched. And so here's what the inverse tangent graph actually looks like. Tangent to the -1 of x. You're going to take that graph and you're going to flip your x's and y's. So now your x's become your y's, which means that this is going to be a -pi/2 and a +pi/2. And when I go to graph it, it still goes through the origin, but it's going to go like this, sideways. Does that make sense? It's an inverse. So you take the x's and y's and you switch them. If you remember how the normal graph goes, you can flip it over on its side and you've got that same idea. Now that is going to help us because we're trying to do this without a calculator and without our charts, right, on how to evaluate these things. So here I am back at my equation and I want to fill in based off of my graph what these values are doing. So let's see what we got. We have the limit. We haven't taken the limit yet. The inverse tangent at 0 is 0. I don't know, I'm not going to fill this in yet. Tangent -1 of a. The limit as b approaches infinity, tangent to the -1 of b, minus, again, my tangent to the -1 of 0 is 0. I think we're close enough to be able to just do direct substitution at this point. So this one's going to be a negative. If I put in -infinity, all right, -infinity, I'm going to -infinity. What is my y value getting closer and closer and closer to? And that would be -pi/2. Plus tangent to the -1 of b. Now I'm putting in infinity. If I go far to the right, if I go towards infinity, my graph's getting closer to pi/2. And so when I add them up, a negative pi/2 is positive pi/2. Pi/2 plus another pi/2 gives me pi as my final answer for that one. Now, is that an example that converges or diverges? And again, you've got a solid answer. It's pi. And so that's going to be a converging thing, if they were to ask you that. All right, you got the steps? So you change it into a limit problem by also changing the bound that's the infinity bound to an a or a b, depending on if it's the bottom or the top. and then you want to integrate it, and then f of b minus f of a, and then take the limit. Cool? Up to there? All right, so here comes the next thing. Do we have time? We do have time. Sketch this graph. They're like, all right, well, here's example 5. Sketch this function, 1 over the square root of x minus 2 from 0 to 5. All right, so here's your situation. You have at x equals 2, 1, 2, you actually have an asymptote. Now you can take your calculator and graph it, but here's what it is, for sake of time. I have an asymptote going here at x equals 2. And the actual function comes down and looks kind of like the can't touch this graph. It goes like this. Now they want me to stop this thing though at 5, so I guess I should put a stopper point right here at 5. And this right here was x equals 2. I guess I should say x equals 5. Okay, so here's my graph. Sketch the graph from 0 to 5. Well, to the left over here, from 0 to 2, there's nothing. You got a whole lot of nothing, which kind of makes sense. Think about it in the function, right? If I put a 0 into the function, I get -2. That would be an imaginary number. You're not going to have a value for that. So it kind of fits and makes sense that you're not going to have values until you get to the right of 2, because that would cause you to have imaginaries in there. So, A, why would from 2 to 5 be considered improper? And the problem is, it's case number 2, you have that vertical asymptote. They're referring to it as an infinite discontinuity, so we'll keep it in terms of, I'm going to put vertical asymptote in parentheses, but really it's because there is an infinite discontinuity at x equals 2. How can you find the area under the curve between 2 and 5 when this part of the area goes up to infinity and there's always going to be a little space there? It never touches a vertical asymptote. That's what makes this whole craziness improper, because you can't, it doesn't close. It's not a closed interval like other ones that we've done. All right, so that's your story with this guy. Now it says, all right, solve the integral. And you're going, okay, well, solve the integral. This one is, what method would you think? Any guesses in the hood?
U sub?
Yeah, good, U sub. Right, so it's a U sub, so we're going to U sub it. I'm going to make my U x minus 2, makes my du 1 dx. Cool. Let's see how it goes here. That means my integral is going to be from t to 5 of u to the -1/2, right? Can I do that all in one place? Are you okay with that? It's this 1 over the square root of u, which is a u to the -1/2, and then du. All right, so I'm ready to integrate that. My power goes up by 1, and I divide by the power. So if I go up by 1, now I am u to the 1/2. And if I'm divided by 1/2, I'm really multiplied by 2. That's going from t to 5. Well, what is u? I can make this even better. So I got 2 times, I guess I like the other bracket there, 2 times x minus 2 to the 1/2 power, going from t to 5. So let's see if we can integrate that. Probably, if I put a 5 in, you can just leave it the way it is. If I put a 5 in there, the first piece is going to be 2 times 5 minus 2 is 3. 3 to the 1/2 is the square root of 3. Can you write that as a 3 to the 1/2? Absolutely. And then the second part's going to be minus, put a t in, 2 times t minus 2 to the 1/2 power. And I guess just to keep it so that they're consistent, if I put the first one in a square root, I should put the second one in a square root, right? There it is. Again, I don't need a plus c because I have bounds. They just happen to have a variable in there. Then it says, okay, well, let's go to the right of this thing. Let's figure out what's the limit as t approaches 2 from the right. So that's talking about this side over here. You can't come from the left because there are no values to the left. We talked about that. They would be imaginary values. You can only come at this thing from the right. There's no other option. The function only exists to the right of 2. So what I want to do is now take the limit. So take the limit as t approaches 2 from the right of, here it is, 2 square roots of 3 minus 2 square roots of t minus 2 Do you remember how you do something when it's a righty-lefty thing? We haven't talked limits for a while. Well, we did L'Hopital, but... So you can take... You want to take a number that's really, 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 really close to 2 on the right-hand side and plug it in. You're going to do direct substitution, but you're going to use something that's really close to 2 and see what happens with it. So if I do a direct, there's nothing to substitute in the first piece. It's 2 square roots of 3. But it's this second guy that gets really interesting. If I do 2 times the square root of t, t is a number to the right of 2. I'm going to go 2.000001. Right? That's to the right of 2. And then minus 2. And I can pick anything I want that's to the right of 2. I just picked that many zeros. Give you the idea. So I have the 2 square roots of 3 in the front. That's fine. Now think about this. If I have 2.00001 minus 2, I have the square root of 0.0000. How many did I use? 1, 2, 3, 4, 5? 5. What is this? This square root. I don't know exactly, but I can tell you it's really close to 0. Right? Yeah, basically 0. Exactly right. So it's so close to 0 that it just zeroes out this last term. I'll put a 0 here. And you get an answer that's 2 square roots of 3, and that is what your limit would be for this guy. That's your part C limit. Okay. Makes sense?
This winner.
Yeah.
Did we fill in the theorem up top?
No, I just was looking at that, Sairaj. I just was looking at that on my thing here. We did not. So it's giving you a clue about functions that are convergent versus divergent if you have it in this form. And what it's saying is it's convergent if your p-value is greater than 1, and it's divergent when your p-value is less than or equal to 1. So in other words, if I had an integral that was, I'm just going to show you what they're talking about. It saves you some steps. If this is x to the second, the 1 over x to the second, like we did on the front page, right? That one we know it came out to be, what was it, 1? That's a convergent situation. Makes sense. Your p-value is greater than 1. It's 2. It's convergent. But if your p-value is less than 1, I don't know that we did any of those, but if your p-value is less than or equal to 1, let's say x to the 1/2. If your p-value is less than or equal to 1, that's an example that diverges. So whatever that power is, and that's only for ones that are in this form. If it's not in this form, like if it was the 1 over 1 plus x squared, that inverse tangent one we did, that doesn't fit this formula, because it has to only be an x being raised to a power. So they're just giving you a diverge, converge shortcut for problems that you're looking at. All right, I believe that is where I want to stop. There are only examples 6 and 7 left. Now let me look for a second. I know for sure that you are able to do numbers 1 through 5. And actually, you probably can do more. I'm looking for you to see if you can do 1 through 5, but you can also do 7. None of these are due, by the way, my children, until after Monday, because we're going to finish the section on Monday. But I'm just telling you so you don't have so many to do at the other end of the spectrum here. So you can do 1 through 5. Number 6 you're skipping. 6 is a skipper. 7 is good for now. 9 is good for now. 11 is good for now. 13 and 14 look good, and that's enough. Okay, so that's about half of them. When we get together on Monday again, I'm going to finish the last couple of examples. We'll talk a little bit more about improper fractions. We'll go over the quiz that you turned in yesterday. And I think some of you did already, but if you choose to make the corrections to the November quiz, you can turn those in to me before the end of the weekend, because we're going to go over those as well on Monday. So we've got a few things to go over. November questions, the quiz. We'll finish these couple examples, and then probably that's going to be enough. All right. Questions or problems from your end? Anything you want to talk about? All right. Have a great weekend.